2 involves limits. Limits of functions of 2 variables. I've got an f defined here, a g defined here. In part A, we're asked to use the epsilon-delta approach to formally prove that the limit of f is 0 as we approach the origin. In part B, we're asked whether f is actually continuous at the origin and to give a reason. And thirdly, we're asked to show that g is not, this function is not continuous at the origin. So that pretty much covers a lot of the limit section that we discussed in lectures. So let's have a look at how we do it. Okay, so this is question 2 now. Let's go with A. So here, f of x, y is defined as the following. So it's sort of defined in a piecewise kind of way. And our limit L is just 0. So what I'm going to try to do is use this epsilon-delta approach and see if I can come up with some sort of proof to prove that the limit of f as x and y approach 0 is 0. So we start with this, and we try to play with it a little bit. Where do you want to see it? Okay, it's all right. All right. So this bottom line, we want to substitute in our f, substitute in our L, and then play with it and get something like x squared plus y squared all square rooted. Okay? That's the thing you're aiming for. You're trying to get this bottom line into something like root x squared plus y squared. That's what you're trying to do. So now, of course, here I'm assuming that x and y are not 0, 0. Okay, so what can I do now? Well, I can obviously get rid of this 0. I can get rid of the absolute value sign from the bottom because the bottom's always positive. So now what? Anyone? Young's inequality. What I would like to do is change this top bit into something involving, say, x squared plus y squared. Then I can cancel off with the bottom bit. Okay? That's what's going through my head. So what I'm going to do, and I showed you this in class, is use an inequality called Young's inequality. Now, Young's inequality is just the following. And this really is gold for these kind of problems. So what I can do is replace in here and here, just replace A with absolute value x and y with absolute value y, so I'll get the following. So this isn't quite a 2 here, but I can take the 2 down there, so I'll get something like this. So now I can cancel off down the bottom. Oh, goodness. I've got what I was searching for. I've got something involving square root x squared plus y squared. Pretty good. So what do I have to do now? Well, I want to choose some sort of delta, right? So this will be less than epsilon when root x squared plus y squared is less than delta. For what choice of delta? Anyone know? Will it work with epsilon? It may work for that choice. There's probably a slightly better choice. Will it work for epsilon? Yeah, it probably will work for epsilon, but there's a more natural choice. Yep. Yeah, 2 epsilon, right? All you want to do is cover up that and make root x squared plus y squared, so that comes up there, and you'll get this. Okay? So the last thing we need to do in these problems is make a choice. We need to construct our delta somehow, and the delta usually involves epsilon. So what does this mean? It means that if you give me any epsilon, I can give you a delta such that those inequalities will work. Okay? So 2 things to remember in the actual dynamics here, I guess. Firstly, you want to transform this into something involving root x squared plus y squared. And the second thing is that you want to choose your delta somehow. Yes? Sorry, say again? Yeah. You've got to change the... Oh, you mean down here? Oh, yes, you may be able to do that as well. Yeah. Like, there are no hard and fast rules with how to do these problems, okay? If you can see another way of doing it, maybe using... And you were using Young's inequality there as well, were you? Yeah, right. So that would have worked as well. But remember, I've kind of taught you two powerful things for limits. One involves Young's inequality. One involves adding things. Like, I remember there was an example last time where instead of like an xy, it was like an x squared up here. And so to get it to like x squared plus y squared, you form a little inequality and you add a y squared in there. Any other questions for this one? Yes?
Is it valid to then go keep the half root x squared plus y squared?
Yep.
Can you just say that's less than root x squared plus y squared would be less than epsilon when epsilon is greater than root?
Yes. Yeah.
Use 0.
Yep. I've sort of compacted it down here. Like you can write more. I haven't sort of. I probably should have written a couple more words here. But as long as you're clear with your solution, that sounds fine. Okay. Any other questions? Okay. So that's part A. Part B. Is F continuous? Why not? Well, probably some of you worked this out. You can do part B without knowing anything about part A. Who knows? Is F continuous at the origin? Who thinks it is continuous? Hands up. Who thinks it's not continuous? Okay. All right. It is continuous. Who can tell me why? So say again? Yeah. Yep. So okay. So the important thing here is that we calculated this limit, we got 0, and that's the value of the function at the origin. Okay, remember, a function's continuous at a point if the limit, as you approach that point, is equal to the value of the function at that point. Okay, so all you really need to do for part B is write down, maybe one line. So this is true part B. Now, you can do part B without doing part A. That's it. Okay? Easy. Part C, show that G is not, so here's our G, show that G is not continuous at 0, 0. So what would we want to do there? We'd want to show that the limit, as you approach the origin of G, is not equal to the value of G, i.e. 0. Can anyone remember a method for showing that limits don't exist? Yes? Yeah, the two-path test. So part C is pretty much just showing that the limit as G approaches the origin doesn't exist by the two-path test. So there's no way that limit can equal 0. If the limit doesn't exist, it can't equal anything. So let's have a go at that. So let's write down our G. We claim this G is not continuous at the origin. So we're going to use the two-path test here. Now, remember the two-path test involves choosing two curves. And as you approach the origin along those two curves, you get different limits. But there's a nice way of rolling all of that into one. So let's approach 0, 0 along the following curves. Now, the one thing with the two-path test is how do you choose the curves? Well, let's look at our function. I've got x squared y, x to the fourth, y squared. What you want to do is choose your function, your curve, be it a line or a parabola or something else. You want to choose your curve so that you get the same powers up here as you do down here. Okay, you want to end up with the same powers so you can cancel off. So can anyone suggest what might we choose, say y equal to some curve? What should our curve be for this one? Alpha x squared. Well, if I put in alpha x squared where alpha is, say, a non-zero constant, I'll get x to the power 4 up there and x to the power 4 in here. So they'll all be the same. Okay? X approaches 0. So I'm going to just sub in for y. Now I can cancel off those x to the fourth. Now, x is approaching 0 here. Alpha has, I can take the limit as x approaches 0. There's no x's in that. So my limit is a function of this alpha, this coefficient alpha. So if I change alpha, if I go through two different parabolas, my limit's going to be different. I'll get two different limits. So by the two-path test, the limit doesn't exist. And so, G cannot be continuous at the origin. So I guess one of the key things in the computation is how do you choose your paths, your equations for your paths? Well, choose them so you get the same powers up the top and the bottom so you can cancel. Questions?